So we say that a sequence of random variables converges to a number A, okay, if this particular expression holds. Okay, let me explain you what this particular expression is. That if for every epsilon positive, chances that yn will take value, you know, either greater than a epsilon, greater than a plus epsilon, or less than a minus epsilon, chances of that goes to 0 as n goes to infinity. So basically, you know, I mean, the idea here is that it will get closer and closer to a as n goes to infinity. It will get closer and closer to a as n increases. Okay, and you know, when n is really high, then the chances that it will take value outside the interval a minus epsilon a plus epsilon, the chances of it taking value outside this interval is going to be very close to 0. Okay, and as n goes to infinity, this will go to 0. Is that clear to everyone?
So screen is not visible.
Oh, screen is not visible. Sorry about that. Oh, it should be visible. I have already. Is it visible to others?
Yes, it's visible to me.
I think you can log out and log in again, maybe if that can help. Okay, so that's convergence in probability. Okay, so now let's consider an ID random variable, sequence of ID random variables. Okay, from that I construct another sequence of random variables, which is known as sequence of sample means. Okay, let me explain you what that is. So basically what we are saying is the following, that we have an ID sample. Okay, these are ID. Okay, now from this we are going to create another sequence. Okay, which is sequence of sample means. So basically the first term in the sequence is the first observation. The second term of the sequence is the mean of the first two observations. Okay, the third term of the sequence is the mean of the first three observations, and so on and so forth. That's a sequence of random variables, because each of them depends on random variable, so it's also a random variable. Okay, and it is a sequence of random variables. Can we say that this sequence converges to some number in probability? That's the question that we would like to answer. Is that okay? Fine. We have seen that, right? I mean, we have seen that, you know, if you toss a fair coin 10,000 times, you know, the proportion of heads will be close to 0.5. Okay, we have seen that if you toss it even further, let's say, you know, 100,000 times, then it will be even close to half. You know, it's very unlikely that it will be far away from half. Is that okay? So does that mean that, you know, and every time it's a random thing, right? I mean, it's not that it's always getting the same value 0.5, right? I mean, we are getting different values every time we sample. Okay, so it's a random variable. So the question is that, can we say that the sequence, you know, the sequence of sample mean, so mean, the sample mean, when the sample size is large enough, you know, has very less dispersion, you know, and as n tends to infinity, this dispersion goes to 0. Can we say that? Okay, and the answer is yes. Okay, so in fact, one way to see that is that if you have this ID sample from, you know, a population with expectation of xi equal to mu, variance of xi equal to sigma square, where sigma square is finite. Okay, and if you look at variance of mn, okay, what is variance of mn? What is it?
Variance of x1 plus x2 so on upon n, so 1 over n square, variance of xi times n.
Yeah, so
Sigma
which is
square upon
sigma square by n. And as n tends to infinity, what happens to this? It goes to 0. Okay, so expectation of mn is mu, variance of mn is sigma square by n. So as sample size increases, the variation, okay, the dispersion is going to be less and less, so it will be more and more close to mn, close to mu. Okay, It will be more and more concentrated around mu. Okay, and therefore, as n tends to infinity, this sequence actually converges in probability to mu. To get the precise proof, this is basically the idea. Okay, to get the precise proof, we can just use Chebyshev's inequality. Okay, so probability that mn minus mu is greater than or equal to epsilon. So basically, this tells you that probability that the sample mean falls outside the interval mu minus epsilon, mu plus epsilon. What are the chances of that? I want to show that these chances diminishes as n increases, and they go to 0 as n increases. Now, by Chebyshev's inequality, this is less than or equal to the variance of mn, which is sigma square by n, divided by epsilon squared. Okay. Now, by squeeze theorem, I know that this term goes to 0, so this term will also go to 0. And this is true for every epsilon positive, no matter how small it is. Okay, and that's basically the idea why Mn converges in probability to mu. That's known as weak law of large numbers. Okay, so this is your weak law of large numbers. Is that fine? Have you understood this? Okay, and that's just a one-line proof. Okay, for weak law of large numbers. In fact, there is also a strong law, which requires, that it converges almost surely to mu. Okay, but the idea is pretty much the same. I mean, that requires a little bit more amount of work to prove it. But this is of course a weaker version of the law, and the idea is the same. Is that fine? Okay. Okay, so this, of course, we can use weak law of large numbers to do a lot of things. As we have seen, we can use it to estimate the probabilities. Okay, probability distributions. Okay, we can also do some integration with it. We can actually do, if you want to integrate some complicated function, we can actually do the integral of that the definite integral of that complicated function using Monte Carlo integration. Okay, so let me explain you that. Is that fine? Okay, and then what we're going to do is we'll just use R to visualize all this. Is that fine? Okay. Okay, so this is another application, Monte Carlo integration. Okay, so let me explain what is Monte Carlo integration. So suppose you want to find the definite integral of this function. Okay, so let me just draw some function. For the time being, let me just restrict the domain to 0, 1. Of course, we can, I mean, this is not something which is required, but just to make things right now straightforward and simple, let me just restrict the domain to 0, 1. And let's say the codomain is also 0 to 1 of this particular function. Okay, and both these can be relaxed. It's not a problem. Okay. Right? And suppose I want to find the definite integral of this function from 0 to 1. Suppose I want to find the definite integral of this particular function, okay, between 0 and 1. So what is the graphical interpretation of the value of the definite integral? Area under the curve, right? I mean, so basically I'm interested in estimating this area. Is that okay? Fine. So I want to find this area. Okay, so one way to do that is randomly generate points from this square. Randomly generate points from this square. Okay, you know the function, whatever function you are interested in integrating. Okay, and then what you can do is the following. Okay, figure out the proportion of points that falls below the graph, and that proportion will converge to the value of the integral. Okay, and the idea is straightforward. So basically what you're doing is, you generate random numbers. So how will you generate random pair of numbers? Okay, so you're going to use R-UNIF twice, for x coordinates as well as y coordinates. Okay, you'll generate uniform random draws for x and you for y's. Okay, and then check where is this point located. Okay, once you have that pair, you check where is this point located and define an indicator random variable I1 if the point is located below the graph. Okay, so it takes value 1 if the point is located below the graph. So basically what that means is if y1 is less than or equal to f of x1, okay, and 0 otherwise. Okay, and likewise you do this for every point. Okay, so you're going to get ij equals 1 if yj is less than or equal to fxj and 0 otherwise. Okay, what is the expectation of ij? It's an indicator. So what is the expectation of ij? It is the probability that yj is less than or equal to fxj. And what is that? What are the chances that if you draw a point randomly from this square, it will lie in this? It's the integral of the function, right? It's the area, right? I mean, area below this, and area is something which is equal to the integral. And that is what we are interested in finding. It's the integral of f t dt from 0 to 1. I'm interested in finding this area. And that's what I'm interested in finding. So I'm interested in estimating this. By law of large numbers, I know that sample mean does the job. What is a sample mean? Summation ij by n. Okay, this will be close to the actual value. So even when you don't know the actual value, you can know a value which is close to it, okay, by doing this, sufficiently large number. And R can do all this for you very easily. I mean, it's not a problem. Okay, let's do some problem where we'll just try and integrate maybe some functions whose integral we know. And then of course we can use the same exercise for integrals for functions for which we don't know the integrals. Okay, so let's do that. Okay, so Monte Carlo integration. Okay, let's integrate x squared, okay, from 0 to 1. So what is the value of the integral of x squared from 0 to 1? 1 by 3, right? Okay, so we should get value close to 1/3. We do this. Okay, so let's just see how we are going to do this. Let's generate a sample of maybe some large sample, whatever, 10,000. Okay. Let's generate x coordinates. Okay. So basically our task is to integrate x squared from 0 to 1. So x, well, R-UNIF. Okay. How many points? 10,000 points. Y coordinates, let's generate, the same way, R-UNIF n. Okay, so now we are going to compare if y is less than x square or not. Okay, so we are going to generate indicators, i's, okay, which is y less than equal to x squared. Okay, this will give me the sequence of booleans, trues and falses. Okay, so true whenever the point falls below the graph, false when point lies above the graph. Okay, and then this is straightforward. Now I want the proportion of points that lies below the graph. So what should I do? Mean of I. That's it. Okay, mean of I. Let's run this. And you can see it's actually close to 1/3. Is that fine? Okay. Yeah. So let us now integrate something not from 0, 1, maybe from 0 to 2. Okay. So how to integrate x squared from 0 to 2? Okay. So of course now proportion will not work, because proportion is always going to lie between 0 and 1, but definite integral value may not be between 0 and 1. So what do you think? What kind of change you should make to this particular thing, so that if you want to integrate a function from 0 to 2, okay, and let's say the values that it can take is between 0 and 3, okay, so what kind of change you should make, okay, so that in this particular analysis, so that you also get the value of the integral when the domain is not necessarily 0 to 1 and the codomain is also not necessarily 0 to 1.
It should be 0 to 2 and uniform 0 to, and potentially y should be uniform 0 to 3.
Yeah, so that is one thing that we should do. Of course, here we should pick random numbers x from 0 to 2, random numbers y from 0 to 3. But then if we are going to do the indicator, still we are going to get the proportion if we are going to take the mean. So what should we do? We have to multiply with what? So just think about it. You have to multiply with some number. So which number you should multiply it with, so that you get the value of the definite integral? Huh? No. 3 into 2, 6. That's 2. Oh yeah, you thought that's 3. Oh, okay, that's not wrong. Then that's fine. Okay. Yeah, so you have to multiply it by 6. Because that's 3, that's 2. So exactly. So it's just like, you've just scaled it up. So uh, uh,
3 into 1.
yeah. So just so whatever proportion you want to get, just multiply it. The area, exactly from which you are picking, from which we are drawing these points, okay, and then you're going to get the value of the integral.
Essentially, what this Monte Carlo integration does is over the domain over which the distribution is defined, it gives a proportion of, like, it goes to the proportion of.
So law of large numbers will give us the proportion.
Yeah.
Because law of large numbers will give the expectation. That's the mean. That's basically the proportion of, that's the probability with which point will fall below the curve. So probability with which point will fall below the curve, for that we can find the proportion through the law of large numbers, then multiply that by the area of the domain cross codomain, okay, and then that's just going to give you the approximate value of the integral. Is that fine? Okay, and this is something that, of course, here we are just using the familiar functions, but you can do it for any. Okay, so let's say if you want to integrate x square from 0 to 2, okay, and so what is the maximum value that x square can take between 0 and 2? 4. So basically we need a box of 0 by 2, 0 to 2 cross 0 to 4. Okay, so area of that is 8. Okay, so x will be r unif n, minimum value is 0, maximum value is 2. Y will be r unif n, minimum value is 0, maximum value is 4. Okay, indicators will be the same, y less than or equal to x squared, because I want to integrate. Okay, fine. Okay, and sorry, let's call this I. Okay, and now we are going to take mean of I, that's the estimate of the probability with which the point lies below this. So that means it's the proportion of area that fall below the curve. So if you want to find the total area, just multiply it by the total area of the rectangle. Okay, so which is 8 times this. okay, and we should get close to the actual value. Okay, so this is 2.65. What is the actual value? Integrate x squared, right? So x cubed by 3, so which is 8 by 3, right? Yeah, you can see it's actually pretty close. Okay, is that fine? Okay,
So
so what?
earlier
Yeah,
while you were explaining, you had mentioned that we have to divide by 1/6 somewhere. I didn't understand that bit.
no, you don't have to divide by 6. You have to multiply the proportion by 6, because proportion, the mean of I will give you the proportion of area that falls below the curve. Okay, that's an estimate for proportion of area that falls below the curve. But you're not interested in the proportion of area. You are interested in the actual area that is below the curve. So if you know how to estimate the proportion of area that falls below the curve, how to find the actual area below the curve, you just multiply it by the total area of the rectangle. Is that fine?
All right, so got it.
Okay, yeah. So yeah, so that's how you do the integration of. So let's do one exercise. Why don't you just estimate the probability that x is less than or equal to -1 and 1, where x is standard normal. So of course, I mean, we can use the p unit. Yeah, so you want to find what is the probability that z is between -1 and 1, where z is standard normal. We know it's 68%, right? But now we want to use Monte Carlo integration by integrating the density function. Okay, by integrating the density function from -1 to 1. Is the question clear? So you have to do the definite integral of the density from -1 to 1 using Monte Carlo integration. Okay, so estimate this using so how should we proceed? So one way to do this is, first of all, realize that it's a symmetric density function. So that's one way to deal with it. We can just deal with 0 to 1 and then multiply whatever we are going to get by 2. So that's one way, or we can just directly use -1 to 1. That's also not a problem. Okay, so let me just do that, 0 to 1 and then multiply it by 2. Okay, so let me estimate the probability that z is greater than or equal to 0, z is between 0 and 1, and multiply that by 2. Okay, fine. So which is equal to 2 times the probability that z is between 0 and 1. Okay, and this is something which is clear from the density function. Density function is actually an even function, so we know that it's is that fine? Okay, so let's find this. Okay, so of course x values will come from r unif 0 1. Okay, fine. So what is the maximum value that the density function can take in the interval 0 to 1? So it can take the maximum value at 0. Okay, so you just have to figure out the value at 0. That is something that you can get by denorm. Right? Denorm will give you the PDF value, the PDF at 0. Okay, so denorm 0. Okay, and that's basically your let's call that L. Okay, fine. Okay, so once you have this, then you're going to do the indicators. Okay, so sorry, you're going to do the uniform draws from R unif N0 L, right? Okay, and once you have that, then that box ready. Okay, and now you want to find the proportion of points that lie below the curve, okay, below the density curve. Okay, so indicators, okay, y is, so there are two ways to do it. If you want, you can write the expression, or otherwise you can also write denorm, because denorm will give you the density, so you just have to compare it with the density. So denorm denorm x. Okay, so you just have to compare with denorm x. Okay, and then L star mean of I should be the estimate. Is that okay? Into, of course, 2, because this is just one side. Yeah, -1. That's right. Okay, let's just run this. Okay, and you can see it's actually close to 68%. Is that okay? So you can actually use Monte Carlo integration as well to find the approximate value of the area below the density function. Okay, over any range, you can just do that for anything. Is that clear? Okay. Okay, so let's now visualize law of large numbers for maybe some problem. Like what we are going to do is maybe just see, what happens as we increase the sample size. Just see what happens to the sample paths. Okay, we can actually do the visualization. Let's maybe use some random variable which we can use. I think in the notes it's exponential. Let me use something else. So let's use Poisson. Okay, so we haven't used Poisson, so let's use Poisson. Okay, so suppose uh, I want to check, so basically what I'll do is I'm going to generate random numbers from Poisson lambda distribution. Okay, and I'm going to look at the sequence of sample means. Okay, I'm going to look at the entire sequence of samples. So I'll basically try and visualize what happens to the entire sequence of samples. I'll plot the graph, and on the horizontal axis I'll put the sample size. On the vertical axis I'll put the sample means, and I would want to see exactly what happens to it. This should converge to the lambda, right? The actual mean, which is the lambda. Okay, so so that is what we should get. Just for visualization, we can just do this quickly. Okay, x is Poisson, let's say, just pick any lambda, let's say 2. Okay, x is Poisson 2. Okay, IID. Okay, we know the expectation of xi is 2. Okay, so what we'll do is we'll first generate random numbers from Poisson distribution. So x is, let's take samples up to 10,000. Okay, x is r poise. Okay, and n. Okay, and what is the value of lambda we are taking? 2. Okay, so once we have this, then we are going to figure out as so the first observation. So basically I'm going to create the means vector. So the first component of the means vector will be the first observation. The second component will be the first 2 observation divided by 2, and so on and so forth. For that, you can use, there's something called cumulative sum, cum sum function. You can use that to actually, so that's going to give you a cumulative sum vector, and then you just have to divide each entry by the sample size, the corresponding sample size, and that's going to give you the cumulative means. Okay, so m is cumulative sum x, okay, divided by 1 is to n. Okay, so right, I mean, because 1 is to n is your sample size, yeah, and cumulative sum will give you the vector of sums, okay, and then you just divide it by this, and now you can just visualize this m and 1 is to n on the horizontal axis, and the sequence of sample means on the vertical axis. You can just visualize this part. So we can use ggplot. Okay. So first, let's create data frame. Okay. Data dot frame. Okay. So size, sample size on the horizontal axis, and that is 1 is to n. Okay. And means, sample means on the vertical axis, and that is given by m. Okay. Okay, so I've created the data frame. Now I'm going to plot it. Okay, ggplot df aesthetics. What is on the horizontal axis? Size. What is on the vertical axis? Means, which is m. Sorry, means. Yeah, just change the name. Okay, and let's just, this is, so let's just connect them by line. So just geom underscore line, and let's run this. Okay, can you see this? Okay, you can see that it's actually, initially there was a lot of variations, okay, but then slowly it just concentrated around 2. Okay, and if you want to actually also add a horizontal line, I think there should be a way to do that. Yeah. Yeah. So y-intercept, so you just have to specify the y-intercept. Y-intercept is equal to 2. Let's put a color equal to maybe blue. Okay, let's just run this. Okay, you can see over here. Is that fine? Okay. I think we can also change the scale. I don't remember the command now. Scale. Yeah. So let's put x-axis on log scale. So what that means is that 0 to 10 will have the same length as 10 to 100, as 100 to 1000, as 1000 to 10,000, so that small sample sizes will be visible more clearly. Because when the sample size is large, it's just uh, actually giving us the same thing, similar kind of picture. Can you see this? This is on a log scale. Okay. Of course, now if you want, you can actually put 10 to the power 6 over here. Okay, and that's going to give you a very good picture, hopefully. Oh, is it too much? Oh, yeah, something happened. Well, it took some time actually. Yeah. Okay. Can you see this? Okay, so you can see that this is for sample size 10, this is for sample size 1000, and this is for sample size 100,000. Okay, is this fine? And you can see that the sample mean, the sequence is actually.
Can you repeat what you were saying about using the logarithmic scale?
Yeah, so logarithmic scale is basically, like, so if you want to actually look at what is happening to the sample mean when the sample sizes are small, a little bit more closely, because if you actually take a sample of size 100,000 and then try and plot it, then beyond 100, so up to 100 will be squeezed in a very small interval. Okay, so you want to see something very clearly, what happens between 0 and 100, then you can use the log scale. Okay, so what happens is that in the log scale, from 0 to 10, it will occupy the same length as 10 to 100, as 100 to 1000, okay, because it's just 10 square, 10 cube, 10 to the power 4, 10 to the power 5. Okay, so is this fine? Okay. Okay, so if you want to add more paths, you can also add in the same graph more paths to see that all the paths will be actually converging to that. So the variations for the small sample sizes will be very high. Variations for the large sample sizes will be relatively small. And this is because of, as we have just seen, that the variance of sample mean is sigma square by n. So clearly, the range of values initially, that you'll observe in the sample path will be higher, and as you increase the sample size, the range of values in the sample mean will actually, become smaller and smaller. Is that fine? Okay. Any questions?